Okay, so welcome everybody. Welcome to the last TPI seminar of 2020. So we're very pleased to have with us virtually Professor Michael Mulligan. So Mike did his PhD at Stanford in 2009, received his PhD in 2009, working with Shami Katru in theoretical physics, and then did some postdocs at MIT, Station Q at UC Santa Barbara, and then back at Stanford for a little while, and then joined the Department of Physics at UC Riverside as an assistant professor in 2016. And so Mike is a field theorist who's worked on a broad variety of problems, both in high energy physics and condensed matter physics. And currently his interests center around the study of strongly correlated metallic systems in 2 dimensions. So like metals or superconductors or quantum Hall systems. And today we'll hear about his work that ties these condensed matter systems to an exciting topic that we heard a bit about at our physics colloquium back in October, where Dan Son gave a talk on the subject of the Dirac composite fermion. So we very much look forward to your talk, Mike. So please take it away.
Okay. Hi. Thanks, Joseph, and thanks everyone for coming. It's great to be here virtually. I'm sorry I can't visit in person. So what I want to tell you about is some recent work over the past few years, and it's about disordered and interacting fixed points of the renormalization group found in composite fermion systems. So what I'm going to be discussing is primarily based on 2 papers. The first is from, I guess, 4 years ago now with Sri Raghu. And then this first paper provides pretty much all of the motivation for what I've been doing in the past few years. And then the more recent paper with Chao-Jung Lee, my student, who's actually a student at Caltech, that will be the basis for the more technical comments that I'm going to make today. Okay, so I wanted to start off and rather simply. So first off, what is this talk about? So the talk really has 2 components. So the first component is a motivation, and really I want to try to give a little bit of a perspective that we're taking, and the perspective is to introduce toy models that we hope will be useful for describing universal properties of disordered interacting systems. Okay, so that's what I'm going to spend half of the time discussing, and then the other half of the time I'll focus on a rather technical solution. Okay, and so in particular examples of renormalization group fixed points. Okay. And of course, stop me at any time. I'm very happy to try to answer any questions you might have. So let me begin by discussing some simple things. So let's consider the electrical resistivity. So I want to consider electrons in a solid, and as we know, we can characterize such systems, at least to some degree, by applying a current and then measuring the resulting voltage, taking the ratio and getting some transport coefficient. And if we consider Fermi liquid theory, that is the framework by which we understand a great deal of behaviors of electrons in solid, and in particular Fermi liquid theory in 2+1 dimensions, so 2-dimensional spatial dimensions, then there's essentially 2 choices that this system has at low temperature. So as we decrease the temperature and consider the electrical resistivity, the first option is that in the presence of impurities and a effective repulsive interaction, these electrons will localize and become electrical insulators. On the other hand, if there's an effective attractive interaction, then it's possible for these electrons to form a superconducting state where instead of the electrical resistance diverging at 0 temperature, instead it vanishes. Okay, so perfect conduction. Those are the two options that the Fermi liquid has at the lowest available temperatures. However, there's a third option when we apply a magnetic field. In that case, we get the beautiful phenomena of the quantum Hall effect, and in particular, the integer quantum Hall effect, in which the Hall resistance, or it exhibits a series of plateaus, step-like plateaus. These numbers, 4, 5, 6, etc., label the plateaus and label the Hall conductivity of these different quantum states of matter, which have finite Hall conductivity and vanishing longitudinal resistance. The lower curves here in this figure correspond to the longitudinal resistance, which, as I said, vanish in these quantum Hall states. Any questions about this so far?
So Mike, just a quick question. So if you had spin-orbit coupling, would something change in your previous slide?
Yeah, so I think with spin orbit, generally there's additional corrections which eventually lead to insulating behavior. I think generally for a non-relativistic electron.
I see. So you would always localize, you're saying?
Yeah, I think so. Okay, so here I'm interested. So that's the conventional wisdom, right? And so here, as Joseph mentioned in the beginning, I'm interested in low temperature metallic behavior, which consequently fails to obey or fails to fall into one of those three categories in insulator, superconductor, or quantum Hall state. And I'll loosely refer to these systems as anomalous metals. So there's two prototypical systems that I have in mind, and they're gonna which motivate the theoretical work I'm going to describe. So the first is occurs in the vicinity of magnetic field tuned quantum Hall to insulator transitions in two-dimensional electron gas. So so there's two plots here. For the next few slides, I'm always going to refer to the right plot first. And so what's observed here is in the vicinity of half filling fraction, instead of say a longitudinal resistance, which is the lower plot here, vanishing for some special magic filling fractions, what's observed is as you go to the lowest of these available temperatures experimentally, the resistance appears to saturate. At the same time of this non-vanishing resistance, there's also a absence of a plateau in the Hall resistance. So the inference is that this state that I've circled here is some sort of metallic state, and it's necessarily anomalous because since it's existing in some disordered interacting system. Okay, so this is a metallic, what's believed to be a metallic phase as a function of some tuning magnetic field. On the other hand, in more disordered TUDEGs, a sharp, what is believed to be a continuous transition is observed. So instead of these fractional quantum Hall effects indicated by these numbers here, instead there's, at least in the vicinity of half fill-in fraction, there's a direct transition between the integer Hall state and an insulator. And if you consider the longitudinal resistivity plotted as a function of some scaling parameter, so you can think of nu roughly as nu minus nu c is roughly as just tuning the magnetic field. That's good enough, as normalized by the ambient temperature. Then these different plots lie right on top of each other, and one can infer scaling and extract some sort of exponent, which is supposed to tell you something important about the continuous quantum critical point. Okay, so in this slide, what I'm trying to show is there's perhaps a metallic phase on the right for slightly metallic phase, and then for slightly more disordered system, there's that phase moves into a metallic point, so it shrinks into a metallic point. Any questions about this phenomena? Okay, let me show you similar behavior, but in a different system. So again, I'm going to be talking about magnetic field-tuned transitions, but in this case, we're looking at superconductor things in the vicinity of superconductor to insulator transitions, and here these are thin superconducting films. And again, I'm going to first look on to the figure on the right here, and what's plotted is the longitudinal resistance as a function of inverse temperature. Okay, so low temperature is now on the right of this figure as opposed to the left. And what's observed is coming in from high temperatures, as you depending on the applied magnetic field, the resistance drops dramatically. This can be on the order of 10 to 100, factor of 10 to 100. And then as you go to at least the lowest observed temperature, there's a saturation of the resistance. And the fact that the saturation occurs for a variety of fields, okay, it moves around a little bit, but it is supposed to indicate again that there's some sort of metallic phase being observed. Now, if you consider, so that was in, quote, clean system. If you consider a little bit more dirtier system, again, this metallic phase, okay, it gives rise to a quantum phase transition, so a sharp, apparently continuous phase transition. Again, so down here, this is the superconductor, in this case, the superconductor or the insulator. And again, scaling can be done on these resistance curves, and you can extract a critical exponent, or more specifically, you can extract some number which has to do with the product of some critical exponents characterizing this phase transition. So the basic picture I'm trying to impart is that there's some sort of roughly analogous behavior in these two rather distinct systems. Any questions about that?
Yeah, that is there something? Is there one critical field? And if so, is there something special about it?
Yeah, it's a great question. So let me. So for this, if you're looking at this left figure, there's one critical field.
Yeah.
However, let me go to the next slide. So I added this slide, which is directly, your question is very prescient. So let me describe this picture, okay? And I think it will at least answer in part your question, okay? Well, okay, let me first answer your question, which is, I don't know, okay? It's not completely clear, okay? But let me explain what I mean by I don't know.
So yeah, let me just say where I'm coming from, because I'm remembering vaguely these old experiments by Alan Goldman, I think, where and they were what were they, a function of temperature, I guess, but it was a question of dimensionality, right? It was the thin filmness.
Yeah, so it's probably like disorder strength. So it's like how thick the film was.
Yeah, and one of them went into the quantum of flux. It came into that value, but the other one did not. And then so they were, I think for a while they were thinking that it had something to do with the flux quantum, but I think that disappeared, right? So this has nothing to do with that, right? Is that?
So I specifically have in mind field tune transitions. Okay. Some of the Goldman experiments that I'm familiar with are nominally about disorder tuned transitions. So these are transitions even in the absence of a field.
Okay. Yeah.
I'm sure he's done also field tuned ones. I'm not sure exactly what to say about that.
Okay, so they're yeah, because it comes in at that critical field, so it's yeah. Okay.
But I will have something to say about your question about how many kind of transitions are involved here. Okay. So I'll say something, okay, which I think is interesting, okay, but it's very much an open question of how to understand and describe.
Okay.
Okay, so what I'm doing, so we were last talking about these thin film transitions, so superconductor and insulator transitions, or superconductor to metal transitions, and what I'm showing here has to do with an apparent, or perhaps more direct, evidence for a breakdown of a conventional quasi-particle picture. So the idea is for quasi-particles, you can, what's one property? Their charge, okay? If we're having some non-zero electrical transport. And on these left figures here, what's being shown, so in the top figure, what we see is as a function of field, again, the longitudinal resistance is dropping dramatically. And there's some region between what's called HM1 here, and perhaps someplace over here, not completely well defined in the figure, where there's a metallic phase. And now what Bresnay and Kapitolnik did is they considered the electrical, the Hall resistivity, okay? So some measure of the, say the charge of this particle, right? And what they found is in this metallic phase, which starts at HM1, let me draw it down here, at HM1, that Hall response vanishes for a finite region in this putative metallic phase, and it starts becoming non-zero again at HM2, okay, and then it ramps up, and eventually you move into some insulating state, okay. Some additional evidence which supports this picture of this quasi-particle breakdown comes from the AC Hall response done by Wang, Tamir, Shahar, and Armitage. Again, the top figure is longitudinal resistance as a function of temperature at varying values of the applied transverse magnetic field. And again, what you see is this precipitous drop by a few orders of magnitude, right? In the lower figure, that's the novel part of this slide here is the AC response, and what you would expect, at least naively, is some sort of cone pole, okay, having to do with this particle in a magnetic field, and what you see no such evidence for any sort of cone pole. Okay, that would be some blip. Okay, in this figure. All right, and this absence of a cone pole, you can think of it in at least one of two ways. One is the effective mass of this quasi-particle is say 1,000 times smaller than the electron mass. A different way of thinking about this is to think about the charge of this particle, and what you would infer, at least if you took the conventional picture at face value, is that charge is 1,000 times smaller than just the conventional electron charge. Okay, so somehow these quote particles, which are giving rise to non-zero electrical conduction, okay, there's non-zero resistivity, longitudinal resistivity, they don't exhibit a Hall effect. Okay.
All right, Mike, so the statement that you'll have the breakdown of quasi-particle picture in the vicinity of the quantum phase transition, or deep in this zero temperature metallic phase?
Yeah, it's good. Yeah, it's a good point. So you might say, well, big, that's obvious maybe at the phase transition, right? And so what I guess I'm emphasizing here is not only at the transition, but also apparently in this putative phase. Yeah. Okay, so this behavior I should say is not understood at all. Okay. Okay. So what I want to argue or persuade is that composite fermions are relevant for both of these sorts of metallic states. So the metallic states found in these TUDEGs and also in the thin films. And the rough phase diagram that these experiments suggest is there's some transition, say quantum Hall, some ordered phase as a function of magnetic field gives rise to some insulating phase. And if you're in, say, a low disorder regime, there's a direct transition, but that direct transition gives rise to a metallic region. Okay. Okay, so so the composite fermion picture, at least for the TUDEG system, would not be very surprising. All right. Since that's where the picture arose. So let me just return to the setup. So we're talking about in the vicinity of half filling. Here I've got a more intricate or complex sort of phase diagram where we see these fractional states. But anyway, we're going to focus on the vicinity inside this red rectangle. And the idea of the composite fermion picture is entirely summarized by this cartoon at the bottom. So the idea is that we trade in some conventional, if you like, picture of electrons, perhaps interacting with some sort of impurities and maybe some electromagnetic field. We trade that in for some new particles called composite fermions, where the electron is equal to the composite fermion plus 2 flux quanta. Now, why is that a useful transformation to make? It's useful because these 2 flux quanta, when the ambient field is oopsie, sorry. When the electron filling fraction is a half, these attached flux quanta that are obtained in this transformation precisely cancel out the ambient magnetic field, leaving these composite particles, composite fermion particles, in 0 effective field. And those particles can, at least in mean field, form a Fermi C and exhibit some finite diffusion or resistance. Okay. So the transformation, the way it works, I'm just telling you in these cartoons, is at half electrical, half filling. That corresponds to the filling fraction for these composite fermion particles of infinity, just they see 0 effective field. And then this picture has been very successful in understanding these strongly correlated, like Laughlin states, 1/3. They're useful because those strongly correlated electron states are viewed as integer Hall states of composite fermions. Any questions about these ideas? Okay, so that's an introduction to composite fermions, the conventional composite fermion picture, and it's probably not surprising to take that point of view, perhaps for this half-filled Lana level, but I'd like to argue that this composite fermion picture is useful, or perhaps useful, for these superconductor insulator transitions and metallic states seen in these thin films. And the key insight has to do with an emergent symmetry of this system. So to describe this emergent symmetry, I have to explain what's called particle-vortex duality. So let me tell you what that's about. So so this particle-vortex duality, as any duality, it's has to do with two different or two apparently different descriptions of the same physical system. So the first system is just some bosons. You can think of these as superconducting or just superconducting Cooper pairs, and they carry some charge normalized to 1 in this Lagrangian with respect to an external electromagnetic field, and then they interact repulsively in some way. These guys carry a charge, and the current is quadratic in these bosons. And as a function of the mass squared of this boson, there's two phases, an ordered phase and a disordered phase. So when the mass squared is positive, it's energetically favorable. Well, there's no order in the state, and so however, when m squared is negative, it's energetically favorable for these bosons to condense, and this condensation breaks this E1 symmetry under which these bosons are charged. Okay, so even though this is really a global field here, I'm going to be thinking about this as a superconductor. Okay, if I wanted to be technically correct, I'd call this a superfluid, but okay, I'm going to abuse the language. Okay, so that's the XY model. So that's for this Cooper pairs, and there's an apparently different theory, which is, you can call it the abelian Higgs model. It looks very similar. So if I just stared at, the underlined in blue part here, I would say that that's exactly the same Lagrangian, and you'd be right, except that now these new bosons, these var5 bosons, are coupled to a little a gauge field, and this little a gauge field is actually a dynamical 2+1 dimensional gauge field. It's not an external field. And then so it has some Maxwell dynamics, and it's coupled to the external electromagnetic field, capital A, in this sort of Chern-Simons or BF form. And what this coupling here tells you is that the electromagnetic current in this abelian Higgs theory is actually related to the flux, okay, of this emergent gauge field. Okay, so again, if you study the mean field phase structure of this theory as a function of the mass, capital mass squared, again, there's two phases. There's one where the mass squared is negative, and that corresponds to a phase in which these fields condense. That actually happens to correspond to an unbroken U1 phase, and then there's a corresponding broken phase. Okay, so these two what appear to be different theories are actually believed to be dual. That is, describe the same universal physics. So they provide alternative or dual realizations of both, not only the two phases, but also of the intervening critical point. That's the critical point that obtains when these mass squareds are tuned to 0. Okay. Now, this picture, this particle vortex duality, gives rise. Not only can you relate the different phases, but you can also relate, of course, observables. For example, the conductivities, and so the electrical conductivity of these bosons in the top, okay, is related to the vortex resistivity. Now, it's possible that at the transition, there's a symmetry between the particles and the vortices. If that happens, then an implication is that the particle conductivity is equal to the vortex conductivity up to a transpose. Okay, that's a technical thing. If this second condition, circled in blue, you substitute that into the one circle in red, you find a condition on the electrical conductivity. So this condition is sometimes called a semicircle law, and it turns out to be observed or realized in these thin films at the transition, and it's realized entirely in terms of longitudinal conductivity. But that realization is a hint that there's a possible particle-vortex symmetry at the transition, and that implies that these bosons and vortices are living at the same filling fraction. That's entirely non-obvious if you were to do a kind of a raw estimate on the boson filling fraction in such systems. Okay, so this is, if realized, it's some emergent symmetry of the system, and the fact that this filling fraction is order one implies that one can make use of a similar transformation that turned electrons into composite particles by attaching 2 units of flux. Instead, we can do a transformation that turns bosons into some composite fermion by attaching 1 unit of flux. Okay, so what I'm going to do in the remainder is I'm going to use some, okay, depending on your perspective, I have recently discovered 2+1 dimensional quantum field theory dualities to study these states. Okay, and the benefit of these theories that I'll discuss is that they manifestly, or they can at least manifestly preserve some of these emergent symmetries of the electron system. So in the thin film systems that we just talking about, that's a particle vortex sort of symmetry. In the 2-DAG, that's a what's called a particle hole symmetry. Any questions right now? So there's quite a bit there in this introduction, but that introduction was really as I mentioned of a perspective that one is taking, and it's actually entirely logical to just start on the next slide and proceed. Okay, so so the basic idea of what's going to happen is I'm going to be interested in 2 sets of dualities, which, like the particle vortex one, related two theories which looked very much different. So they had different, what I'll say, microscopic or UV Lagrangians. However, they had the same universal physics. So the first theory that I'm going to consider for the first duality is one that controls an integer quantum Hall transition. So in the first theory that I'm circling right now, that's just the theory of a free fermion. That's all I've written down, free Dirac fermion. And as I'll review in a second, as a function of tuning of the mass of this fermion, it realizes some integer transition. So this picture is the long wavelength description of some electrons hopping on some lattice with some particular flux penetrating it. Okay. So there's an alternative description of the system in terms of some composite fermions. These are composite Dirac composite fermions, and just as in the conventional composite fermion picture, there's some flux attachment and some sort of 2 flux attached to each Dirac particle. That's roughly how one can think about it. So that's one duality that I'm going to be thinking about. The other one I'll be thinking about, and as you'll see, I'll be able to think about these 2 simultaneously. It has to do with the superconductor insulator transitions. So I'm going to begin. So one frame is this XY theory, which we already talked about. And instead of thinking about a dual vortex theory, I'm going to consider a dual fermionic theory. And now if we stare at this, if we stare at this Lagrangian, it only differs from the top one by the presence of some sort of Chern-Simons term, but it's very closely related to LF. Okay. So let me first describe the phase structure of this theory. Actually, I'm only going to describe the phase structure of the first theory. Okay, so this is some theory that describes an integer quantum Hall transition. And what I'll focus on here is just trying to convince you that this lower theory describes an integer quantum Hall transition. And it's a transition as one varies this mass parameter in this model. Now the duality tells us that this capital mass is somehow is related to this lowercase mass, and so at least in mean field theory, as I vary this mass through 0, I'm going to get some sort of quantum phase transition. So if I stare at the mass here and I take it to be positive, I claim that corresponds to an insulating state. So my conventions are such that when M is positive, the low energy theory governing this dynamical gauge field little a and the electromagnetic field capital A takes this form. And if one would say if you integrate out the little a gauge field, what you get is a purely Maxwell term for the electromagnetic gauge field, electromagnetic field, which describes an insulating behavior. The point is this sort of term in an effect of Lagrangian gives rise to vanishing conductivity. On the other hand, if the mass is negative, again, there's some conventions here, but the low energy effective Lagrangian that governs the remaining degrees of freedom below this mass scale is what I've circled. And what you can see is in this final equality, we have a term which describes integer quantum Hall conductivity. So there's vanishing longitudinal conductivity and integer Hall response. Okay, so this first duality, at least the dual theory, and so also the direct theory, it describes an integer Hall transition. Similarly for the second duality. Any questions before I get start to try to study these theories in more detail?
Sorry, Mike. The second one, the one with the bosons, it's just another dual of the XY transition.
That's right. Yeah, yeah. So if you want, there's three guys which are all due to one another.
Okay, the fermionic dual of the XY transition.
Yeah, and so the way you should think about it is attaching a single unit of flux.
Oh yeah, and then you just do like the composite boson picture.
It's like the inverse of the composite boson, kind of. Yeah.
Yeah. Okay.
Other questions? So maybe I'll just say one word. I mentioned that these. I said some comment that these are recently discovered dualities, depending on your perspective. So these theories were actually studied in the early 90s. Okay, the novelty, which I'm maybe only going to mention in the final slide, is that these duals are part of a larger duality web. So a larger set of theories which are dual to each other, which include not only theories with abelian gauge symmetry, but also non-abelian gauge symmetry. Okay. Okay, so what I'd like to do, so I've just tried, or at least I've just stated that I've got two types of transitions, an integer quantum Hall transition and a superconducting insulator transition. what I want to now consider is what are the effects of two things on these transitions. The first is the effects of a Coulomb interaction. And the second is what's the effect of impurities. And there's a number of simplifications that I'm going to be making. Okay, the key simplification, which I've already alluded to in my previous analysis, is these transitions that I'm going to be considering have to do with mass-tuned transitions. So I've already described it, so it won't seem it won't be surprising. But if we have in mind the motivational, systems, right? Those are field-tuned transitions. Okay, describing finite density matter. Here I'm considering mass-tuned transitions at zero density. Okay, and so this is, well, you might think of this as a sort of warm-up problem to to a system at finite density. So that's the main simplification in this study. Other simplifications are a bit more technical. So the first is that these theories that we on previous two slides, they're strongly coupled theories. Okay, because these composite fermions here, they're called psi, they're coupled to some dynamical gauge field, which I'm calling little a. And that dynamical gauge field is a strongly coupled object. And so to try to tamper that guy down, we're going to make use of some sort of large flavor expansion. So we're going to introduce a number of fermion species labeled by capital I. And at large flavor, the interactions between these fermions and the gauge field can be made weak. Okay, and so our results can be trustworthy. The last part of this theory, which is describing just a clean system, is that I've introduced a new parameter which I'm calling theta. Theta allows me to continuously, in principle, interpolate between a fermionic system and a bosonic one. So when I mentioned that I can study these two transitions on the same footing, what I meant is that I can, by a choice of theta, whether theta is equal to 1/2 or theta is equal to 1, I can study that integer Hall transition or a superconductor insulator transition. And for general theta, one would have an anionic. These sides would describe anions. Any questions so far? Okay, so that's the first part of the model that we're going to consider. So that's just the clean system, and now we want to add some things to it. So the first thing we want to add is a Coulomb interaction, and in particular, we're going to add a dissipative Coulomb interaction. So this anion gas, which is this crossed part of this figure, we're going to imagine that there's some 2-dag plane living just below it, and the interaction of these fermions down here via some instantaneous Coulomb interaction is going to lead to some dissipative a dissipative force between these composite particles. So the way this works is that generally this Coulomb interaction, this instantaneous Coulomb interaction mediated by this tilde, a zero field, in 2+1 dimensions, the inverse effective interaction just goes as k, the momentum. This 2-dag is going to, in some cases, screen this Coulomb interaction and give rise to another term such that the entire inverse effective interaction takes the form that's circled. Now, duality allows me to translate this effective interaction into the composite fermion frame. And it turns out that this Coulomb interaction gives rise to some additional kinetic term for this emergent gauge field. And the only thing to stare at, perhaps, is that without this dissipative plane, so when the sigma E parameter is equal to 0, we have the quote standard Coulomb interaction, which would just be parameterized by this momentum K. But in general, there can be corrections to this. That's the Coulomb interaction. And now let me introduce some randomness, some impurities. And so there'll be a number of impurities that I'll consider, but let me first just consider two sets to begin. So the first is you call it a random mass term for the composite particles. And the different impurities that we can add are, they're constrained by symmetries that we choose to preserve. These are discrete symmetries, charge conjugation and time reversal, or their product. And this first symmetry this first type of randomness will play a major role. And so this is the random mass disorder, and it preserves charge conjugation, but it breaks the time reversal invariance. Another type of randomness, sometimes called topological randomness, is if you have a random quenched scalar potential that, say, the electrons couple to, the way that couples to the dual particles is it couples to the flux of this dual field, okay? And this sort of coupling is sometimes called a topological sort of coupling. It will turn out that that a lot of these types of randomness, at least for our superconducting system, that preserve time reversal don't lead to any sort of accessible fixed point. And it's really something that is poorly understood. So here we've got in this dual fermionic dual frame for our superconductor for our XY model. You see there's some Chern-Simons term, a dA term, and that naively breaks a time reversal symmetry, right? If we don't think too hard about it, and it turns out that that this theory, if it's dual to this XY model, somehow the time reversal symmetry, which is naively broken, has to be an emergent property of this theory. And this emergence ends up not being visible in our analysis. Okay, that's a bit of a technical comment, but I'm pointing it out. Okay, so I've discussed two types of randomness. There's actually a host of other sort of random terms. I'll just underline what we've discussed, that term and this other term, but there's three other types of randomness. And we'll study this randomness with a conventional sort of replica trick, which allows us to calculate disorder average quantities at the cost of introducing a replica and believing an analytic continuation. Okay. Any questions so far? So the rest of this talk is to just, I want to tell you the results, okay? So we've got three terms. So we've got a clean transition, either an integer Hall transition or superconductor insulator transition, and now I want to consider the effects of Coulomb interaction and disorder on that transition, and ask it, are there any interesting fixed points that obtain? So it's quite a complicated model. We already kind of saw that with all the types of randomness, 5 types of randomness that we were actually considering. But there's other terms. So let me, all the coupling constants, the things that determine whether or not there's a fixed point, some metallic state, are given in this table. And some of the ones that are important let me just introduce you to them. So the first one is this Wx parameter that parameterizes the strength of the Coulomb interaction. There's a new parameter, sorry about the now introducing a new parameter here, I'm calling kappa. That's analogous to our theta parameter, which tells us whether we're describing fermions or bosons. And then there's a number of other parameters which have to do with the disorder, okay? And roughly what we're trying to do is when we study these, whether or not there's a fixed point where we want to try to relate bare and renormalized couplings. And from that relation, we want to understand a flow in coupling constant space and ask if there's any places, fixed points of that flow. And if there are fixed points, we're going to they correspond to quantum phase transitions, and we're going to characterize them by two exponents. The first is a dynamical exponent. That's something that relates frequencies to momenta, excuse me. And then the other exponent that we'll think about has to do with the correlation length exponent called nu. And because these are mass-tuned transitions, at least the ones that we're thinking about theoretically, that's controlled by this mass operator. So let me tell you the results of our study. So so it turns out there's two general classes of possible fixed points. The first are classes where the effective Coulomb interaction, this repulsion, is finite, and another class, which I'll describe momentarily, is when that interaction grows very strong. Okay, so but before we get to that, it's useful to kind of just a reality check or a zeroth order check, where we don't include any disorder and we just include some Coulomb interaction. And so if we look at the beta function, or something that controls the flow of the Coulomb coupling, we see that it's negative. This negative sign corresponds to a term which is irrelevant in the renormalization group sense, so not important at long wavelength. And what that tells us is the clean fixed point is stable to a Coulomb interaction, and we can check what the various critical exponents are, and we find a match to previous work. Okay. Now let's start to add the Coulomb interaction. And what I've written here is when we include disorder which preserves a charge conjugation symmetry. So what I'm thinking about is random mass disorder that's characterized by this coupling G sub m, and then you remember W sub x corresponds to the Coulomb interaction. And if we stare at these figures, so if let's see, so if this randomness here is set to 0, then we know that we're going to flow back to the clean fixed point. Okay, but once once the disorder is turned on, starting this lower left here, we're gonna the random mass disorder says that we're going to flow to some random critical point. That's what this green dot corresponds to. But now once we're there at some random mass disorder, it turns out that this Coulomb interaction is now a relevant perturbation to our system, and we flow to a new fixed point indicated by this red dot. Okay, these other figures, so the rightmost one, now whether we flow to some non-trivial fixed point or not, or we're just stuck at the origin, depends on whether we're considering the fermionic theory, integer Hall transition, or the superconductor insulator transition. At least in our analysis, the integer transition doesn't admit any non-trivial disordered fixed point. So these left and middle figures correspond to the superconductor insulator transition. And at least for those within our analysis, we find some non-trivial fixed points. Okay, so now we can ask, what are those, what are those exponents that are supposed to tell us something about that system? And so for the green fixed points here, that's the ones with 0 Coulomb interaction. We find that the correlation length exponent is 1, and the dynamical exponent is 1 plus some correction, 1 over n correction. And we can compare that to some recent work, both theoretical, that studied the XY model with random mass disorder, and then some numerical work from a little bit earlier, a few years ago. Okay. Now the red fixed point, as far as I'm aware, there's not another study of that, and for that one we find that both the correlation length exponent and the dynamical exponent are fixed to 1. This is really the main, I would say, the main result of our work. I'll describe a few other examples, and then I'll conclude. So I mentioned that at least in the superconductor insulator transition, the Chern-Simons term in that theory naively breaks time reversal, and what that technically leads to is various runaway flows, and so we don't find any interesting behaviors anymore for the superconductor insulator type of transitions described by composite fermions. And so, however, we can still study the Dirac, the integer Hall transitions. It turns out that for those transitions, we can have a non-trivial fixed point that preserves some product of charge conjugation and time reversal, and it's actually a fixed line that depends on some parameter that characterizes that topological disorder that I mentioned a little earlier. And there's a set of critical exponents as before. Z in this case is fixed to 1, and the inverse correlation length exponent is 1 plus a correction. Okay, let me describe for you what I meant by the two classes. So I mentioned there was two classes of sort of fixed points. One where the effective Coulomb interaction was finite, the other one where it was infinite. How you can understand it is by staring. Actually, let's just stare at the top one here. So this W that characterizes the Coulomb interaction, and its running is summarized by just its classical engineering dimensions. And so the fixed points that with finite Coulomb interaction always corresponded to Z is equal to 1. But of course, it's possible in principle for Z to be greater than 1, in which case this effective Coulomb interaction can go to infinity. Now that seems bad, right? But if we remember what are the terms in this Coulomb interaction, not only is there the strength of it, but there's also a dissipation parameter, and it runs an identical way to the overall interaction. And at least when both of these parameters grow strong, it's the ratio that appears in the action, and their ratio can function as a marginal or just, if you want, just a parameter, which can be varied. And so we find there's a non-trivial for this infinite Coulomb example. There's a non-trivial fixed point for at least this random mass disorder for the superconductor insulator transition theory. That these fixed points are pictured here by these red dots, and at least along this line, the correlation length exponent is equal to 1, and the dynamical exponent is some continuously varying number between 1 and 2. We don't find infrared stable fixed points for the integer Hall transition. Okay, are there any questions? Okay, so let me just summarize. It wasn't too long ago on the slides, but I would say the novel finding, I think, in our work has to do with this this fixed point that obtains for random mass disorder and a non-zero Coulomb interaction. It's actually a line of fixed points parameterized by the dissipation parameter, that sigma sub e parameter. And what we find is both these exponents are equal to unity. So it'd be very nice to have some sort of check on that. Okay, so let me conclude by just by mentioning some questions. I have 3 here. So the first is, so we did an analysis in a large flavor expansion, and it at least by comparing to other works, it seems like the large flavor expansion here, at least the leading order, could be improved upon. So perhaps higher order corrections would be useful. Now, this is a large flavor expansion, but it turns out in the duality web that, here I've just taken one example, this theory of a free fermion is dual not only to a theory of composite fermions interacting with an abelian gauge field, but also there's a whole infinite class. Okay, so this one theory here is dual to an infinite number, at least apparently, composite fermion theories, which are labeled, if you want, by a UN gauge symmetry. Now, once you have such a gauge symmetry, you naturally think of other kind of artificial expansion parameters. So it's natural to consider a 't Hooft expansion. And a question which I'd really like to know the answer to is, does this 't Hooft expansion somehow provide a better approximation to the strong coupling dynamics of interest? Okay, so that was another that's another technical question. Okay, a really important question is I simplified our model to something that deals with only zero density of states, but can we generalize this to systems with a finite density of states? That's would be apparently required if we want to make any sort of contact with the experimental systems of interest. So that's a very important, outstanding question. Okay, that's all I've got. So I want to thank everyone.
Okay, thanks very much, Mike, for this very interesting talk. Do we have any questions?
Can you just elaborate on that last point? I guess I missed the non-finite density of states. Where did that come in, and what would be involved in generalizing that?
Yeah, let me see. So let me scroll back. So so this is an example. So one way to understand this top model comes from thinking about some electrons hopping on a lattice with some flux.
Yeah.
And it turns out that the long wavelength description of that is a density tuned transition in the electron frame has a description as a mass tuned transition in the affected theory. Okay. But so that mass tuned transition gets incorporated into a mass tuned transition in this dual theory, which I've focused on. But what I'm if we want, I think, to try to describe say the 2-DAG, okay, then we want something where the filling fraction is a half, and that translates into here with that these composite particles are at finite density. So their density here. And that's, so the transition would not be strictly a mass tune transition, but it's really a field tune transition. And that's really an entirely different kind of beast. What this lower theory would naively, how you would analyze it is, once these fermions are at finite density, then they, at least in mean field, they form a Fermi C. And then we include the interactions.
So this is like a single particle picture. That
I'm starting with a single particle picture, mean field picture, in the hopes that that's useful, right? Yeah. And then I'm trying to add what the additional ingredients in this theory are. Let me think.
Maybe are you saying that in a sense you're really interested in some non-relativistic electrons that have a certain density, but then there's a plateau transition there, but then you're mimicking that by a problem of Dirac fermions, where you kind of you're at zero density, and then you kind of your chemical potential is at zero in your Dirac model, but in reality you're really kind of interested in a system that has a finite Fermi C in the field.
Yeah, I mean, if I strictly stare at this model here, right? So it's perfectly fine for this top theory to describe. So this is the insight of Sun, okay, where we can describe half-filled Landau level in terms of Dirac electrons, and the transition occurs by changing, either the density of these electrons or by tuning the field. Okay, and that transition is not a mass tune transition. Okay, and these dual particles here. Okay, you do one reason why you do the dualities, because you don't want to deal with Landau levels. Okay, you want to start with a Fermi C state. Okay, and then try to do perturbation theory about that if you can. These dual particles are at finite density, and the whole dynamics of the theory is drastically changed when that occurs.
But is there, so suppose you were considering graphene, quantum Hall effect in graphene, and then you were at charge neutrality,
mm-hmm.
And would that model then be kind of more correct? Would it be closer to the physical situation if your physical system was graphene at charge neutrality?
Yeah, that's probably, I would say that would be a reasonable thing to consider. Yeah.
Okay, any further questions?
Yeah, I have a question.
Sure.
Just a couple questions. So first one is just kind of the general picture. You sort of identified like an insulator, superconducting state, quantum Hall, and then now you have these so-called, quote, anomalous metals. My first question is, are there other exotic things beyond that? I mean, your analysis is kind of designed in some sense to explain some of the experimental features.
Mm-hmm.
But is there other things beside anomalous metal, like a fifth or sixth state, other states?
Well, I guess, so I'm focusing on things kind of classified by electrical properties, right? So I'm clearly ignoring like spin, if we just think about what are the properties of the electron, right? So spin and charge, okay. So there's a whole spin class, which I'm ignoring here, okay, which would be interesting. But let's continue to ignore that maybe for your question. So there's a whole, of course, host of exotic topological states of matter, okay? And you could, so maybe perhaps something that's surprising is, I'm talking about these integer Hall transitions, okay, to insulator or superconductor to insulator. You might think those are rather, well, because they are conventional states of matter, right? But the intervening critical points are, I would say, poorly understood theoretically. So, but if you were interested in other sorts of phases, then in 2+1 dimension, there's a lot of exotic topological states. Yeah. So, but yeah, what I'm interested in here, as you mentioned, as you said, is generalized types of critical phenomena. Okay. Mm-hmm. So I'm asking what sorts of generalizations exist, and trying to explore that. Mm-hmm. I'm not sure if that answered your question.
Yeah, no, I think it does. Yeah. Mm-hmm. Okay. And then just a short second question. Just again, I'm not so familiar with some of these systems. You used anion for, you had S, dividing it into S1, S2, S3, and then why do you use the anion?
Yeah, that was more of a convenience. That's just a convenience. So the thing was, you might have said, make a choice, right? You're talking about integer Hall transition or superconducting transition. Why talk about them both? Pick one and just stick with that, right? You could have said that. Okay, don't complicate your life, right? And so what I'm emphasizing here, I guess, is two things. First is these transitions, the superconducting insulator transition and the integer Hall transitions, which occur in different physical realizations, right? They perhaps admit similar theoretical descriptions. Okay, what similar means technically is that there's some kind of effective Hamiltonian, and the way that these effective Hamiltonians differ is primarily by this parameter, which I'm calling theta here, and that theta is, if you want to call it an anion statistics sort of parameter, where by varying this thing from 1/2 to 1, I can change the statistics of the particles that I'm describing. Okay. You can either describe fermions at one end, so 1/2, or bosons when it's equal to 1, and in between they don't have a well-defined. Well, they don't have a boson fermion statistics, but that would be more an anion.
Got it.
So there's that technical convenience, which I would say is not as important, okay, although it's there and allows me to consider both simultaneously. But I think the physical importance is that that there's these emergent symmetries, I would say, are leading me to this physical theory. Okay, so that's perhaps a new jumping off point. So if Fermi liquid theory is useful, obviously, and now we want to try to find new points about which to do perturbation theory, if you like. Okay. So this Lagrangian is supposed to be a new point, a departure.
Good. Thank you.
Does that make sense?
It makes sense. I got it. Yep.
Okay. Yeah. Thanks.
Okay, so I think we should probably stop here. So let's thank Mike again for a very interesting talk.
Thanks, everyone.
Thank you.